I want to talk about something called conservation of momentum. This is a conservation law. In science, when something is conserved, that means that the amount you start with will be the amount you finish with. If you're in Chem 11, you've probably learned about conservation of mass. In a chemical reaction, you can't gain or lose mass. You can just transfer objects from one form or one compound to another. Well, there's something similar in momentum, but first, let's start with collisions. In the collision seen below, which vehicle experiences the larger force? The truck, the car, or both the same? First of all, I'm going to abbreviate. I'm going to use capital T for truck and capital C for car. Div, which one experiences the larger force? The car experiences the larger force. Is that correct, folks? Which one experiences the larger force, folks? Why is it the same? Okay, forces come in pairs. Which one of Newton's laws is that? If you know that's the third, you can write that. I saw three of you go like this. So I'm thinking many of you should write forces come in pairs. However, if you knew that was Newton's third, you can write Newton's third. Forces are the same. Now, the reason you said the car, you were getting mixed up between force and damage. So, example 2, why is it that the car and the car driver are almost always worse off as a result of this collision? If the forces are the same, why isn't the damage the same? No, they take the same force. Yeah. They have a different mass. How would that affect? I agree with you. How would that affect things? You know what? Let's, first of all, we agree force of the truck is the same as the force on the car. Technically, there should be a negative in there because they're opposite, but I'm just going to look at the magnitude. Okay. Banner, F equals what? Laura, which one has a bigger mass, the truck or the car? So the truck has a really big mass, really tiny acceleration. The car, smaller mass, it has to have a big acceleration so that the forces match. And I've taught you what does damage in an accident, not force, not velocity. What does damage in an accident? Acceleration. It's all about reducing the acceleration. That's why if you're watching the news and there's an accident on the freeway with a car and a semi-truck, often you'll hear the semi-truck driver walked away unharmed or was taken to hospital for observation. But you often won't hear good news about the car driver. Oh, they're cutting this person out with the jaws of life, and the firefighters aren't rushing because there's no use. Okay? Forces come in pairs. I have to give you some terminology. Underline closed system. A closed system is one that's cut off from the outside world. There's no F applied coming from off the page. The only forces in a closed system are the ones that the objects that you see are applying. Some examples, frictionless surfaces like ice. If ice was perfectly frictionless, Christian, it would be a pretty good closed system. Deep intergalactic space where you're away from gravity, that's a closed system. Floating on the water, if there's no waves, if the water is nice and smooth, that's nearly frictionless. That's almost in real life a closed system. Not quite perfect, but in our magic physics world, it is. And then rolling objects, which we're not going to look at much this year. So what's a closed system? There's no outside forces. It turns out for collisions in a closed system, these contact forces, when they collide, are governed by Newton's third law. What does Newton's third law say? Div, forces come in pairs. If force is equal and opposite, that implies that impulse, that momentum change, that delta P, momentum change, impulse is equal and opposite. Alexia, how can I prove that? So the forces are the same, F1 equals F2, but opposite, there's the negative. But because they're part of the same collision, Tristan, the time has to be the same for both objects because they're part of the same collision. If the collision stops for the first object, it stopped for the second object too. So we can multiply by time, and this is still a true statement. From your formula sheet, what's force times time? Delta P, which is change in, what's P in a brief for, folks? Momentum or impulse. This means that the change in momentum, the impulse, they come in pairs. They're equal but opposite in the collision. Let me elaborate. What does that mean? If the car loses 20 units of momentum in that collision, what can we say about the truck, Cole? If the car loses 20 units of momentum, what did the truck do? No. If the car lost 20 units of momentum and the momentum is conserved, what did the truck do, folks? Gained, not also lost. Truck had to gain 20 units of momentum. Okay? Because forces come in, everybody, pairs, and because time is the same, that means impulses come in opposite pairs. That means when one object loses momentum, the other object what? Gains momentum, same amount. It means that momentum is conserved. The momentum for the system is not gained or lost, it is transferred from one object to another. Don't write this down, look up. In English, we say this: the amount of momentum that we start with equals the amount of momentum that we end with. You all know me. This is why I said don't write this down. Will I ever write out the English version of this rule again? No, I'm going to abbreviate. Here's how we're going to abbreviate it. This is how you can write it down. Don't write down the English version. First of all, we have a basic. What's my abbrev for the word equals? Be stupid obvious. Okay, so I can put an equal sign. Who's in pre-calc 12 here this year? Okay, you've seen an abbrev for the amount or the total. It's this symbol here, the Greek letter sigma, and this means the sum or the total. So the total amount, I'm going to, oh, by the way, when you type font it, the Greek letter sigma looks like that. It kind of looks like a capital E that's been stepped on. It's where our letter S comes from. When you handwrite it, everyone just puts a capital M on its side. We don't do the little serifs or anything like that. We write it like that. Ooh, and Laura, what's my abbrev for the word momentum? What symbol have we chosen? What abbrev have I used for what we start with all year long? Don't overcomplicate it. What letter as a subscript have I used for the amount we start with all year long? Initial has to equal the final. That's the law of conservation of momentum. Tristan, write it down. Written as short as possible. The total momentum you start with has to equal the total momentum you finish with. Did I give you this on your formula sheet? Can you go look? I did? Yeah. And then this year I did something I don't normally do. I think I expanded it because momentum is, Christian, what times what? So if you look at your formula sheet, I said, where I wrote this, I said, oh, that's going to be M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final if there's two objects. This is the law of conservation of momentum. Except we're going to cut corners when we get good. Wait a minute, Mr. Dueck. Yes, Tristan. You're telling me that the amount of momentum I start with is equal to the amount of momentum I finish with. Yes, I am. But Mr. Dueck, in this collision, both cars came to a stop after the collision. Folks, if they both came to a stop, what's their final momentum exactly as a number in your head? Okay, so let's write this down. Final momentum is 0. Mr. Dueck, that means the initial momentum had to be 0. Yes, it does. But they're moving. Oh, okay, let's see if we can prove this. Let's see if we can figure this out. Again, I'm going to use T for truck, C for car. Christian, momentum is what times what? So before the collision, I have mass of the truck, velocity of the truck initial, and mass of the car, velocity of the car initial. After the collision, they all came to a stop. Okay. Christian, no, I picked on you already. Let's go with Nate. What's the mass of the truck? What's the initial velocity of the truck? What's the mass of the car? Listen closely. What's the initial velocity of the car? Be very careful. See if you can impress me. There's a candy for you if you can. I'll give you a hint. It's not 24. What's the initial velocity of the car, folks? Shaz. What? We've got to pay attention to direction this unit. Right? It's in the opposite direction of the 10. How would I show opposite direction? Negative. And if you type this into your calculator, you don't need to. You know what you're going to get? You're going to get 24,000 plus negative 24,000. In your head, Nate, you know what 24,000 plus negative 24,000 is? Like I told you. If the final momentum was 0, that means the initial momentum was 0. It was. They canceled each other out perfectly. Now, in real life, usually vehicles skid after the collision. Now it's no longer a closed system. So when we're calculating collision speeds after collisions, we're talking about right after the collision before they started skidding. But we can now start to analyze collisions. What's the law of conservation of momentum? It says in any collision or explosion in a closed surface, momentum is, here's your fancy word, conserved. What does conserved mean in science? What you start with is what you end with. The momentum can't be created or destroyed. It can be transferred from one object to another, but I'm telling you, the total you begin with equals the total you end with. This rule, Alexia, can be written in several ways. In English, the total initial momentum of a system equals the total final momentum of a system. Using some symbols, momentum initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. Using some Greek symbols, I often write this down because it's the least amount of writing and it gets my mental juices flowing, but you'll notice I will get good enough, I won't always write it down, or the expanded version, since momentum is mass times velocity. When do we use the law of conservation of momentum? When there's a collision or an explosion. You know what? I read that wrong. I should have said it this way. We use the law of conservation of momentum when there's a collision or an explosion. In short, we use it when there is a jeune. Then you want to use conservation of momentum. I have a lovely toy. I have to pause the video. Sorry for those of you who are watching on YouTube. Let's do some examples. Today, we're going to look at comic strip picture examples. Friday, we're going to look at word problems. So let's do this one together. Nick, you and I are going to do this one together. I see a picture. First of all, is there a collision? Yeah, that's what the doink is supposed to represent. So we're going to use conservation of momentum. What does it want me to find? The missing velocity. I'm looking at all the velocities here. Which one has a question mark next to it? Which one is missing? VA final or VA initial? Okay, so this is the one that I'm going to try to find. So folks, Nick and I are going to walk through this together. You're all going to piggyback along. Nick, is there a collision? This is a job for conservation of momentum. So I'm going to start out by writing the sum of all the momentum we start with equals the sum of all the momentum we finish with. The total momentum we start with equals the total momentum we finish with. I write that down just to get the juices flowing. I write that down just to get the juices flowing. Thank you for picking up the hint. Okay. Christian, momentum is what times what? It's mass times velocity. I'm going to remember that. Before the collision, Nick, what's moving? Car A, car B, both, or neither? Looks like they're both moving. Are they stuck together or are they separate? Well, they're at different velocities, so they must be separate. But I always ask myself that question next. Christian, how do I calculate momentum? So I'm going to argue before the collision, we have the mass of car A, velocity of car A initial, and the mass of car B, velocity of car B initial. That's the amount of momentum we're starting with. Both are moving. Is that all right? Okay. Wham! They collide. After the collision, Nick, what's moving? Mass A, mass B, both, or neither? I think both, and I don't think they're stuck together because it's suggesting that this velocity is different from this one. And in fact, I don't even know which way the car is moving. It's got an arrow on either end. But I can show that. I can say afterwards, car A, mass A, VA final, has momentum, and car B, mass B, VB final, has momentum. The amount of momentum I started with, Tristan, equals the amount of momentum I finished with. Nick, what did you say they're asking us to find? There's two VS. Put a dot above it. What side is the VAF on? Left side or right side? Right side. So what's going to drop down like a domino? Left side. Remember doing our formula manipulation? This drops down. Then what? Remember, Ryder, it's reverse bed mass. We do our adding and subtracting, then we do our multiplying, dividing. So, Nick, what do I want to move over next? I need to deal with this thing. How will I move it over? How do you know? Yep. Minus mass B, V, B final. Okay, I've taken care of that. The last thing I need to take care of is this M in front of the V. And then if you don't mind, Nick, I'm going to put the VA final over here by itself because that's where we usually write the thing by itself. We're done the hard part. Now it's just careful plug and chug. You've all got good calculators partly for this reason. This is one of the reasons I yelled at you at the beginning of the year. Nick, I've scrolled down. Oh, pay very careful attention to direction. Nick, what's mass A? How big? What's VA initial? Plus, what's mass B? What's VB initial? What? What did he say negative 2? He's correct. Why? Look at the picture. It's in the opposite direction of 10. How would I show opposite? Negative. Then I have a minus. You said car B was 2,000. What's the final velocity of car B? I couldn't hear. Final velocity of car B. I couldn't hear. Oh, 4? Positive or negative? Positive? To the right? Because what Nick has decided is to the right is positive, to the left is negative. Divided by 1,000. What do you get? Once you've written that down, you want to go trundling off to your calculator. Is this a fraction? Yep. Is there more than one thing on the top? Either your fraction button or brackets around the top. Don't need brackets around the bottom. I might be able to do this in my head. It's going to be 10,000, take away 4,000 is 6,000, take away 8,000 is negative 2,000. In my head, I'm getting negative 2. Double check me. I don't think it's negative 11. Negative 2? I think I'm right. In terms of direction, what's the negative telling me? You know what? I'm going to use right and left. You could use forwards and backwards. I'll use right and left. So I'm going to go 2 meters per second left. Figure out where you typed it wrong. If not, we'll try the next one. Oh, you missed a 0? That'll do it. Yeah. Turn the page. This is going to be our procedure, except I'll turn these into word problems. You'll know there's a car crash. Often, Cole, you'll have west and east or north and south, which means you need to let one way be positive and one way be. And it's the amount of momentum beforehand equals the amount of momentum afterwards when there's two objects. Cole, let's you and I do this one. We have a collision, so it's going to be conservation of momentum. So I'm going to write the sum of all the momentum I start with has to equal the sum of all the momentum I finish with. Before the collision, what's moving? Car A, car B, both or neither? Stuck together or separate? Looks like they're coming towards each other, so they can't be stuck together. So before the collision, how much momentum am I going to have? Christian, momentum is what times what? So I'm going to have mass A, velocity A initial, plus mass B, velocity B initial. That's how much momentum I have to begin with. Yes? Yeah. They collide. Sorry for those of you on YouTube who are using headphones, but you're awake now, I'll bet. Cole, after the collision, it looks like separate because they gave me both velocities and they're different from each other. So I'm going to have the mass of car A, velocity of car A, final. That's a final. And mass of car B, velocity of car B, final. Okay, now I've scrolled down. Cole, what are they asking me to find? We had a question mark next to it. I have two VAs. Okay, that right there. Again, when in doubt, I put a dot above the thing that I'm trying to get by itself. It just helps me zone on it. What side is that on? The left side. What side's going to drop down like a domino? This is going to drop down like a domino? I disagree. Which side's going to drop down like a domino? The side that doesn't have what I'm looking for, because it's not going anywhere. It's going to stay where it is. Good. Now what? Now I'm going to do my adding and subtracting. So now I'm looking at the left side. What do I need to add or subtract? Good. VB initial. That takes care of this bad boy here. Now what? Yep. And now paying careful attention to negatives and positives. By the way, again, if you're a little stuck, you might even before you start go, hey, that's negative. That's negative. That's positive. Oh, and I think because here they didn't put arrows on either end, I'm expecting a positive answer because they kind of with the arrows suggested that. So now, if you want to read the numbers out to me, VA initial equal. What was the mass of car A? And a final velocity of car A. Which one of those is correct? Mass of car B. Final velocity of car B. Minus 2,000. Initial velocity of car B. All divided by, and I forgot to put an A there, the mass of car A, which is 1,000. Once you've written that down, you can go hustling off to your calculator. I should be able to do this in my head because it's all thousands. It's going to be negative 2,000 plus 8,000 is positive 6,000. Zero? No, no, no. There's a minus minus. That's a plus. So it's going to be 6,000 plus 6,000, which is 12,000. I think you're going to get 12. Double check me. Yep. So 12 meters per second. And since it was positive, I'll just say, yeah, to the right. On a test, I'd probably, instead of giving you a picture, I'd give you easts and wests with the, or norths and souths with the velocity, and same dealio, you'd let one be positive, one be negative. So these two, A and B, this is how I would do it on a test. Where would I cut corners in my homework? Okay. Chaz, like this. Example C. Is there a collision? Yeah. Oomph. What are they asking me to find? This is going to be conservation of momentum. I'm not going to write the sum of all the initial momentum equals the sum. You can. I'm going to skip that step because this is how I do it in my homework. Then I would say to myself, self, before the collision, what's moving? Separate or stuck together? So I might feel comfortable jumping straight to momentum is mass times velocity. So mass A, VA initial, plus mass B, VB initial. By the way, common silly mistakes that I see, students put a minus here and they want to go final minus initial, final minus initial. That's for change in momentum. That's for impulse. This is not an impulse question. Wham! They collide. After the collision, looks like they're stuck together. How would I show stuck together? I'll give you a hint. It's a word that starts with letter B and rhymes with rackets. I'm going to go bracket, mass A and mass B are all traveling V final. Close bracket in front of the V final. Darian, that's how, kind of like we did M all A, that's how I would show the mass of all of them times V. What am I trying to find, Chaz? Okay. By the way, what if they wanted V final? Divide by the bracket. Divide by the mass of both of them. Okay, VAI, I'm going to put a dot above it again. What's going to drop down like a domino, Shaz? First of all, what's going to drop down like a domino? That. Start with that. Then we do our getting the VA initial by itself. Now what? All over what? If this was a test, I would now write out the numbers. I'm doing my homework. I'm trying to see how good I am and where I can cut corners. I might try being bold enough to go straight to my calculator. So I've got the numbers kind of right here. If I get out my calculator, ooh, Shaz, is this a fraction? Is there more than one thing on the top? I would definitely put brackets around the top. And then I have a little mini bracket. I actually have to open a bracket and open a bracket. Even those of you with your fraction button, you'll still have to do the mini bracket. And it's going to be 2,000 plus 4,000. I close off the mini bracket, Alexia. Then I have V final 5 because they're stuck together. Oh, some of you, especially if you have a sharp, you might have to go times 5. On my TI, I know I can get away without the times sign. I can put a number after a bracket, and my software knows to multiply. The sharp and some of the older Casios might not. Then I have a minus sign. Mass B, 4,000 times mass B initial, -3. Have I reached the end of the top? Close off the top, divided by mass A, which was 2,000. Can I do this in my head? It's going to be, oh yes, I can. It's going to be 8,000 times, it's going to be 21? No, I'm way off. No, maybe I'm good. 21? Positive 21? Direction. Yeah. I would never do it this fast on a test. This is what I might try in my homework to become an expert. Last one. Thank you for your patience. I'm old. Yeah, we know, Mr. Dueck. Shut up. When I was a kid, we didn't have video games. Wow, you're that old, Mr. Dueck? One of the games we used to do when I was about 7 years old, we called it ghost riding. This is when I had my first bike. You remember your first bike, the one that had no gears and that you would stop by pedaling backwards because it didn't have brake, like it was a really basic kind? It was, for me, it was the, oh, Solomon, I always had an electric bike with gears and a chauffeur. Shut up. So the bike that I had was one of those kiddie bikes. This is the game my friends and I used to play. We used to ride in a parking lot. There was a school nearby. We would get going really fast. We called it ghost riding. You would jump off the bike, run beside the bike for a while, and then try and jump back on before the bike wiped out. That's what this person is doing. We have a bike and a rider, but I'm going to be even more general than that. Here's what I notice. We have one piece breaking into two separate pieces. That's an explosion. It's not an explosion of the type that goes bang really, really loud. It's an explosion of pieces falling apart. And that's what I really mean by an explosion. One piece turning into more than one piece. So is there an explosion? Yes, this is a job for conservation and momentum. But I can notice a few more things as well. So Adam, look up. How fast was the rider? Oh, I like the fact that this question uses R for rider and B for bike. Yeah, you're right. I should ask Ryder this question. We'll ask Ryder the question about the rider. Uh, R for rider, B for bike. Pick letters that make sense. Don't just stick with A and B. If, for example, there's an arrow and a target, how about A for arrow, T for target? If there is a bullet and a gun, B for bullet, G for gun. Anyways, Ryder, here's what I want you to notice. How fast, before he or she jumps off, how fast is the bike rider traveling? After, how fast are they traveling? Did they gain momentum or lose momentum? Be stupid obvious. But because momentum is conserved, that means the bike must have gained momentum. The bike is going to be going faster than 5. I can tell you that right now. When I solve for the final velocity of the bike, which is what they want me to find, give me more than 5. Not only that, the rider only lost 3 meters per second, but they have a bigger mass. The bike has a smaller mass, but it had to gain the same momentum. The bike is going to be going faster by more than 3 meters per second. I can tell you that right now too. I can make some predictions. This bike is probably going to be going in the close to 10 or maybe even in the teens. All right, Ryder, here we go. Is this a collision? Say no. Is this an explosion? Technically, yes. We're going to use conservation of momentum. If you want to, you can write, you don't have to, but you can write the sum of all the initial momentum equals the sum of all the final momentum. I usually do on a test or a quiz because it gets my brain thinking the right way. Before the explosion, what's moving? The bike, the rider, both, or neither? Stuck together or separate? How am I going to show stuck together? Looking for where it starts letter B, folks. Okay, so before the explosion, I have in brackets mass of the rider and mass of the bike, the initial. Whoa! After, I think separate, yes? I'm going to have mass of the rider, velocity of the rider final, and mass of the bike, velocity of the bike final. Ryder, what are they asking me to find? Okay. What side's going to drop down like a domino? What side is what I'm trying to find on? Starts with letter R. So what side's going to drop down like a domino? Starts with letter L. I always do that first because I like to write something mindless-ish down. Now we do our adding and subtracting, reverse bed mass. So now what? Which mass? Yeah. On a test, I would write out the numbers. Oh, in my homework to see if I can, maybe I would try going to the numbers here. So it's going to be V bike final equals. If I was typing this in, I would say, okay, it's a fraction. brackets around the top, or use your fancy fraction button. But all of us are going to have an open bracket. Mass of the rider, was it 60? And then plus 20, close bracket, times, what was the initial velocity of everybody? 5? And then minus mass of the rider, which is 60, times final velocity of the rider, which was 2, I believe, yes? Close off the top, divided by mass of the bike. Okay, do this one in your head. Sure, I can. It's going to be 60 times 20. That's going to be 60 plus 20, 80 times 5, 400 minus 120 is going to be 280 divided by 14, I think. Double check me. 14? Yeah. Positive or negative? Yeah. So which means the bike sped up going forwards or to the right. 14 meters per second to the right. Remember the predictions that I made? I said the bike is going to speed up, yes. And I said it's going to speed up by more than the 3 that the rider slowed down. Why? Bike had less mass, so you got to have more change in velocity to get the same momentum change. Is that all right? Is that right? 14, everybody get 14 meters per second? All we're going to look at next class is word problems involving this. For now, if you want to, you can try every question. Really, your goal for Friday, come back Friday having tried everything on lessons 1, 2, and 3. See if you've wrapped your brain around the concepts of momentum, of change in momentum, of impulse, of final minus initial, of F delta T, and M delta MV final minus MV initial. And impulse equals impulse. Folks, I'm going to pause the video. Actually, I'm going to end the video.